So let's talk about network covalent atomic solids. This is where we've got atoms covalently bonded to each other throughout the solid. So carbon is one that forms this. Elemental carbon can exist in several different forms. These are called allotropes. There are other elements that also have allotropes. Sulfur and phosphorus are two that come to mind. You can have the pure element in different forms. So one form of carbon is graphite. In graphite, the carbon atoms are covalently bonded to each other, and they make these hexagons, interlocking hexagon rings, and there are sheets of hexagon rings, and then those sheets lay on top of each other. The sheets are held together by dispersion forces. And since we have a wide area, a large area on these surfaces, they hold together pretty well, but the dispersion forces are significantly weaker than covalent bonds. So if you put some pressure on this or stress on this, the dispersion forces are going to give way and slide apart. The covalent bonds are going to stay intact. You have graphite in your pencil, okay? Your pencil lead is not made out of lead. It's made out of graphite. There's no lead in your pencil. So graphite is slippery. It's a good writing substance. You know, you move it along the paper. Those dispersion forces give way and leave bits of the graphite behind so that you can read it later, right? It's useful as a lubricant. You can get powdered graphite and spray it into a lock, and it'll get all over the place and act as a lubricant. You got something squeaky and you have a pencil on you, you can actually just rub the pencil in the squeaky part and lubricate it that way. Graphite's a good electrical conductor as well. So if we look at each of these carbons, how many bonds do they have? So there's one hexagon, and there's another one going to be over here. So looking at this carbon, how many bonds does it have? How many lines come out from this circle? 3, thank you. Okay. So one of the suggestions in my teaching evaluation is I should be more Socratic. I don't know that that really means what he thinks it means, because we're not really discussing and disproving theories and ideas. I think what he meant is I should ask you more leading questions. The thing is, when I ask you questions, nobody answers, right? So I can't stand around with awkward silences. So I was just testing that out there, and that didn't work very well. Okay, back on topic. So this carbon has 3 covalent bonds. How many covalent bonds does carbon like to have? 4. So what's going on here? What's with the 4th one? Well, we did hybridizations, right? And so this would be sp2 hybridized, and then there'd be an unhybridized p orbital with an electron in it. And so what happens with these graphite sheets is you have delocalized pi bonding or extended pi bonding network that goes across the sheet. And the electrons in that pi bonding network can move, and that's what's conducting electricity in graphite. Graphite has a density of 2.2 grams per cubic centimeters. No, you don't need to memorize that. If you put it under very high pressure, you can squeeze or force the carbon atoms to form a more compact structure, such as a diamond. In a diamond, we see some of this hexagonal pattern thing again, but now we have covalent bonds in all 3 dimensions, not just in 2-dimensional sheets. A diamond has a density of 3.5. It's larger, more dense. So diamonds form naturally underground. You know, you go and you mine diamonds in Africa. I don't think there are any diamond mines here in California. You can also synthesize them, but it requires a tremendous amount of pressure and heat. So like 50,000 atmospheres of pressure. That's like mind-boggling. And 1,600 degrees to get the graphite to rearrange into carbon. The diamond unit cell is similar to that zinc blend. So in the zinc blend, we had sulfide ions in a face-centered cubic, and then we had zinc ions in 4 of those tetrahedral holes. In a diamond, you have carbon atoms in the face center, but then you also have 4 carbon atoms in the tetrahedral holes, and they're all covalently bonded together. So in this diamond structure, we see that the carbons now have 4 covalent bonds, and so they're pretty happy with that. Diamonds don't conduct electricity, though, because there's not that pi bonding network for the electrons to move. So they're kind of stuck. Diamonds have very high melting points, 3,800 degrees Celsius. Diamonds are very hard, and so they make an excellent cutting tool. I mean, they're very pretty on your finger as well, but they make an excellent cutting tool or an abrasive, because when you cut something like with a circular saw, or when you're polishing something, there's a lot of friction and heat builds up, right? And so you need something that can withstand high temperatures. It needs to be harder than the thing that you're cutting. And being an excellent heat conductor is also helpful because it can help conduct the heat away from the surface that's being cut or polished. Any questions? Another form of carbon was discovered in the 1980s by aiming a powerful laser at a carbon surface. And you might ask, well, why did they do that? To see what would happen. Scientists are curious. I know that many of you are curious too, because there's some things that you'd like to try in lab, but we just can't because they're not safe. Yeah, you go get a PhD in chemistry, get your own lab, and then, you know, provided you don't blow things up and get the university on your back, you can almost do whatever you want. It's kind of fun. So, you know, this happened. These are called, this one is called Buckminster fullerene. There's a reason for that name. I'm not going to go into it. They're soccer ball-shaped clusters of 60 carbon atoms. So we've got this 60 carbon atom ball-shaped molecule, essentially, because it's all covalently bonded together, 60 carbon atoms. You can make them in other sizes, it turns out. You can make ones as small as 36. You can make them that are more than 100 carbons. And so in general, they're called fullerenes, but their nickname is buckyballs because they're ball-shaped and Bucky, short for Buckminster fullerene. So those are kind of cool. Graphene oh, there's the word. I knew it was in here somewhere, graphene. So this graphene nanoribbon. Graphene, that's the substance that we talked about in the first section of this chapter with the Friday night experiments that they discovered and got a Nobel Prize for. So this graphene ribbon or a graphene sheet consists of the covalently bonded carbon atoms in this big two-dimensional sheet. It's essentially one layer of graphite. Graphite's a whole bunch of these together, but graphene is just one layer. It is one atom thick, and because the atoms are so tiny, it's actually transparent, which is kind of cool all by itself. And so, of course, you know, what can we do with this? Well, you can make nanoribbons, you can make sheets, you can make tubes out of this stuff. So it looks a lot like chicken wire. So imagine just taking a roll of chicken wire and bending it around and fastening it to itself. And you've got this tube. This is called a nanotube. You're going to have a single-walled nanotube. You can nest a bunch of these inside of each other and create multi-walled nanotubes. All kinds of cool things that you can do with this. Nanotubes are awesome because they're 100 times stronger than steel, but 1/16 as dense. So you can get something that's stronger and lighter. And when you're talking about like cars, airplanes, even things like golf clubs and bicycles, very strong and very lightweight is an excellent combination. So when you see something like maybe a golf club that has a graphite shaft, it's not made out of pencil leads. It is carbon, but it's more likely these nanotubes of carbon. Very strong. Because this is that really a two-dimensional with the extended pi bonding, these are conductive, and so you can make really tiny wires out of bundles of nanotubes. Any questions? Another covalent atomic solid, a group of them actually, silicates. So silicates contain silicon and oxygen. So this isn't an element, it's a compound. But it's an atomic solid because the individual pieces are atoms that are covalently bonded to each other. They're just not all the same atom. A molecular solid would have individual molecules that are held together by intermolecular forces. This is all held together by covalent bonds. It's the most common network covalent atomic solid. It makes up about 90% of the Earth's crust. Sand is mostly silicate. So you know there's lots of sand around, right? It's very common in ceramics, cement, and glass. We're going to talk about what makes those different from each other. So when we say silica, that has a formula unit of SiO2, which means that in the entire structure, the ratio of silicon to oxygen is 1 silicon to 2 oxygens. Quartz is one form of silica. You can have other forms as well. So this is the structure of quartz. And we see here, if we look at the oxygens forming a tetrahedron, then the silicon is at the center of that. When we draw it out like this, it looks like that's SiO4, doesn't it? But notice that this oxygen has a lone electron there, an unpaired electron. That oxygen is going to bond to another silicon. And this one's going to bond to another silicon. And so they're going to go through like that, and it's one giant molecule, essentially. Any questions? So a lot of what you should know about this part is these words in bold. Those are vocabulary words. You know, what is silicate? What is silica? What is quartz? I'm not looking for extensive details here, but just a clue, basically.